Thanks for joining us today for what will be our final webinar for 2015. Rest assured we'll be back next year. So without any further ado, we'll get stuck into today's topic, which is compressed air systems, looking at how to get started when looking to identify opportunities to save not just energy, but capital and maintenance costs as well. Okay, so just to start off today, we're going to talk about just a very quick review here. Why are we even worried about compressed air? In fact, you can go to many sites and compressed air is probably so far down the list of priorities that it does indeed often get forgotten, as it says down the bottom there. But energy costs, particularly electricity costs, are increasing. Despite where you might sit on the whole climate change debate, the reality is every bit of energy we use is some sort of emissions component attached to it, even here in New Zealand. Now, depending on the nature of your industry, anywhere from 10 to 40%, or in some cases even more, of industrial electricity usage, it can be spent on compressed air. And typically, when you look at a lot of compressed air systems, it's not uncommon at all to find an easy sort of 20 to 30% saving that can be achieved at relatively cost-effective rates of return. There's been some instances with savings of over 50%. So it's one of the classic examples where something's often forgotten, as we say, sort of it's referred to commonly as the forgotten utility. Because it's often forgotten, there's plenty of opportunities on just getting a few basics right can make all the difference. So with that in mind, we just want to start out today with a very, very quick sort of definition here and understanding the difference. We're going to talk a lot about demand and supply. So the beauty of a compressed air system, unlike fans or pumps or even steam, is it's a what we'd refer to as an open system. We generally compress the air over in the plant room in our air compressors, and it gets sent through some sort of distribution system, gets used, and we have a very loose sort of recycle loop where the air is obviously discharged to atmosphere, and then back in the plant room the compressor just sucks more air in. And so what we tend to do is we split the system up into two main sides: the supply side, which is everything there in color, which is effectively our compressor. So looking here at our compressor here, obviously we have a dryer in this particular situation, a couple of filters. It's a filter here after the compressor, another one here after the dryer. We have a receiver, and generally after the primary receiver, we would consider everything downstream from that our demand side of the system. Now, of course, if you're operating a facility or manufacturing site with a compressed air system, typically you're going to have a maintenance contract with in most instances a vendor or supplier, and they will be responsible or have some sort of contract to maintain not just the compressors, but the receivers possibly, but certainly dryers and filters and so forth. What's interesting, of course, is in many instances those contracts don't go outside the compressor plant room. And as we'll go through today, some of the biggest gains are to be had further downstream. And in fact, we're going to talk about today where we start, why we start there, and what the pros and cons are. So just to really reiterate, we have the supply side where the compressed air is generated and treated, and in some cases stored, and then obviously the demand side where it's used. And oftentimes as your sites get bigger, you have a significant or substantial distribution component joining the two together. The beauty, of course, is that once the air is sent down the line, generally you don't need to worry about it coming back like you would with sort of steam and condensate systems. So just to really get stuck in today, the demand side, in looking at what our potential is, well, number one, top of the list is air leaks. It's sort of become the cliche. Everyone knows that air leaks are an easy win, yet the irony, of course, is it's a bit like common sense. It isn't always as common as you might think. Just because we know air leaks are an easy win Doesn't mean that they always get done, and indeed many sites will start with a hiss and a roar, get on top of their leaks, but of course they keep coming back. So anywhere from 10 to 50% is not uncommon in terms of your total demand being a leak rate. Now, incidentally, the Department of Energy in the US a number of years ago, their best practice guideline for an air leak rate for a site was 10%. In more recent years, that's been dropped to 5%. Interestingly, they don't say zero, meaning that if you've got no leaks, you may well be actually overspending on your maintenance. The next one is artificial demand, and we're going to define this a little later, but effectively the demand that shouldn't be there. Once again, that can be anywhere from 5 to 50%. Peak load reduction, i.e. We can have some systems, and it could be down to how they're operated, how they're used, how they're managed. We can have very, very high peaks for short periods of time, which has some rather disastrous consequences on the overall operation of the system. Okay, then we can look at system pressure, and we can reduce that system pressure. We can save not only at the compressor in terms of the power used to compress the air, but also we then have a knock-on reduction in the volume of air that we use. So in summary, all of these things are going to deliver energy savings. They're going to deliver emissions reductions. There's maintenance savings, and we haven't got it up there, but ultimately in the long term will also potentially deliver capital cost savings. So why are we going to start with leaks? Why have we put leaks first? Well, it's very, very important, especially with a compressed air system. You always, absolutely always want to start with the demand side first. Now, the great thing with leaks is they're very quick wins. They have a really short payback. Many instances, it can even be less than 3 months. On a lot of larger sites, you can find where you've got multiple compressors. It's not uncommon that when you start fixing your leaks, you actually turn whole compressors off. And so not only do you then start saving your energy, you then also start saving on your maintenance costs. Then longer term, you've got capital cost savings as well. Great thing with leaks is they're always there, so you have a base load energy reduction. Okay, can lower your maintenance costs, as I've mentioned. Now, on this point, it's really, really important. This has come up more and more of late in regards to why a lot of sites, when we have sort of an open and frank discussion with maintenance managers and the like, and they all know it's important to fix leaks, but there's a number, and scarily a number of sites, and quite a few of them, where they know they should fix the leaks, but they're in a quandary. They've got a fixed R&M budget, and that's the money that's needed to fix the leaks. The problem is there's no feedback loop that the money they save from fixing those leaks doesn't come back into the R&M budget, because that's over in the energy budget. And so the energy budget looks great, but if you're a maintenance manager that's already had some costs cut out of his budget and he's had to do more with less, if you've got a precious materials budget and you've only got so much there and you've got to manage and keep everything else going, there is a real conflict in that. As much as they would like to fix those leaks, they need those funds to be spent elsewhere on actually maintaining the plant and keeping the plant running, as opposed to saving some energy. And so I really want to hammer this point home today, that if you're in this situation, we need to help you in some way to be able to communicate this and get this message clearly in front of the right people, because the leaks are gonna, when you fix them, are gonna deliver a real tangible net benefit to the bottom line this year. But it's very important that that loop gets closed so your R&M budget doesn't get cannibalized and left short to fix the other problems and challenges that are inevitably going to arise. So very, very important to understand the link between the R&M budget in terms of fixing leaks and the energy budget where the reward is delivered. Okay, so moving on, once you've fixed your leaks, what do we do then? And so really it's back to looking at where else are we using our compressed air and how else can we eliminate the demand that's not really necessary. So eliminating artificial demand and then eliminating inappropriate uses, managing our peak loads, and then ultimately dropping our system pressure. So let's start with artificial demand, and we'll start with a very simple definition. We define it as an excess demand above what is actually required. So what does this really mean? Well, what we're saying is whenever you're using air, if you're using that air at a higher pressure than you actually need to do that task, i.e. especially unregulated end users, okay, you will use more air than you need to, okay, because flow is directly proportional to the absolute pressure. So if you think about it, if you've got a valve or some other cylinder that's actuating, it needs a minimum pressure to do so, and it's important that we have that minimum pressure, otherwise we can have valves lifting off their seats, and that can cause all sorts of other serious ramifications. So we want to make sure we have sufficient pressure, but if we have substantially more pressure than we need, we're going to use a lot more air than we actually need to, and we'll go through some examples to highlight that. So here's the first case scenario. We have a pneumatic control valve. Now they might typically have a specification that requires 4 or 4.5 bar gauge air. Now if you're running a 6.5 to 7 bar gauge system and you're not regulating that pressure supplied to the control valves, every time that valve is actuating, you're using or filling that volume of whatever cylinder or actuator that's being operated with 6.5 or 7 bar instead of 4.5 bar air. Now admittedly you don't want to be right on the limit, so you want to be a little bit above it, but a question for you to think about today is what's an acceptable safety margin? Now a good engineer is going to understand and appreciate that there's safety margins or factors of safety, or a little bit of wiggle room, if you like, because we obviously want to have safeguards in place. In many respects, you might think of that extra pressure as an insurance. Now the question is how much insurance do you need? Can you over-insure? And so let's look at the scenario. So if we need 4.5 bar and we supply it with 7, okay, well, we can probably get away with a 5 bar gauge supply. We want to, have half a bar headroom is probably fairly comfortable. Okay, so what would be the equivalent savings? Now remember, we have to add 1 to both pressures. Okay, so 5 bar gauge becomes 6 absolute and 7 becomes 8, obviously. Our demand is going to be directly proportional to the pressure, and so we can actually save 25% of our demand on that valve by supplying it with 5 bar instead of 7 bar air. Now if we supply it with 6, obviously fairly straightforward, our demand reduction is 12.5%. So I want you to think about this for a minute. So if you've got valve banks, okay, and they're actuating, by simply regulating the air pressure to that valve bank, you can reduce your air use by 25%. 25%. That's a substantial sort of penalty that you pay through simply some lazy engineering or system specifications. Do you really need that much insurance? Now, obviously, if you're going to drop your pressure to those valves, you need to make sure that you don't have a potential exposure to a risk if you drop some pressure instantaneously for a short period. So you might need to think about some safeguards. Now, obviously, the easy, lazy safeguard is just crank up the air pressure. The problem is not only when you crank up the air pressure do you use more air, it costs you more to make that air. And so the alternative is looking at some extra storage, making sure we've got good control systems in place, the right backup capacity, so that in the minute it might take for another compressor to kick in, for argument's sake, you've got enough storage in your system so the pressure doesn't drop too far or too low. And so just to reiterate, the savings figure on the previous page were actually just purely a demand or flow rate reduction. Remembering that compressed air flow was measured in normal or actual cubic meters, cubic feet. So what we mean by that is the equivalent air at the atmospheric pressure. Now there's different standards to what you can use. We're not going to go into that today, but in simple terms, you're measuring the air as it would be expanded back out to atmospheric pressure. Now what happens, of course, is when you drop your system pressure, your air compressor doesn't have to work as hard, and for a 1 bar reduction in discharge pressure at the compressor, depending on compressor technology and how the compressor is being controlled and set up, conservatively 6 or up to 9% reduction in power consumption per 1 bar reduction in the discharge pressure. So not only can you get the demand saving reductions, but you then also get a power consumption or compressor efficiency gain, and those savings multiply. Okay, so looking at a second example here, we have pneumatic conveying or blowdown. Now we might use, for argument's sake today, 3 bar. Now if we're supplying 6.5 or 7 bar, do we really need this much margin? What safeguards do we really need? So to just really highlight the farcical nature of this sort of solution, if you're using 7 bar when you can be using 3 bar, okay, our 3 becomes 4 bar absolute, our 7 bar becomes 8, and so our demand saving is literally 50%, or in other words, you're using twice as much air as you actually need to. Now if you regulate your air down to 3.5 or 4 bar respectively, you can have a 43 or 37% reduction in demand use. Now bear in mind that none of those figures include the power consumption reduction at the compressor if you're compressing the air to a lower pressure to begin with. Now obviously if you're going to do this, you need to make sure you've got enough storage and system controls, safety isolations. What happens if you lose your pressure? Does something block up? Now the other thing, of course, is in these sort of applications, you should not really be using 6 or 7 bar instrument air for this sort of application. You should be using a dedicated low pressure blower, a low pressure compressor, or alternately, do you really even need the 3 bar? Can you substitute that with a high pressure blower, which will have a substantially lower specific power consumption? So these are the sorts of things to really challenge if you're using compressed air to blow things around, in terms of pneumatic conveying. Is that really the best solution? It's certainly probably the cheapest capital solution when the system got installed, but long term, what's the total life cycle cost for running and operating that system? Okay, so this last one we're going to talk about is actually what happens to your leak rate in your system as you use a higher system pressure. And so this is something that's often forgotten about or neglected, and that is when you have your system across your site, especially if you've got a large site, every leak that you have is going to lose more air the higher your system pressure. And so that insurance margin that we talked about earlier, where one of our simplest solution is crank up our discharge pressure at the compressor, means we've got a bit more headroom if something happens. If we lose some air pressure all of a sudden, nothing's going to happen. So obviously, receivers can get expensive. It's not uncommon for a decent sized receiver to be sort of in the vicinity of $20,000 or $30,000. And so obviously they can get expensive to install, and so when you're trying to trim a capital budget, they're an easy thing to eliminate. They're a big target and they make a big difference. And so when you cut those out, you think, well, let's just add another half bar at the compressor and we should be all right. Well, what we want to just run through really quickly here is let's look at what this actually means. So if you need 6 bar in your compressed air system, but because you've not got enough storage in the system and because you're wanting to make sure you don't get too big a drop in pressure before your next compressor kicks in if it needs to, we're going to run at 7.5 bar gauge at the compressor at the supply. Now what of course that means is instead of producing 6 bar or 7 absolute, you're running at 8.5 absolute, which means every bit of leak across your site is going to leak 17% more than it needs to. Okay, so what I want you to think about for a minute here is, if you've got that 1.5 bar increase in system pressure to compensate for other deficiencies, it means that every bit of use across your site, and especially your leaks, are losing that much more, i.e. 17%. Okay, now if you drop to 6.5 bar, you're now down to 11%. Okay, if you drop only to 7 bar, you're still sort of saving 6% or 5.9%. So an immediate drop in that pressure is an immediate win in terms of reduced leak rate. Never mind also the power saving at the compressor. So how do we make savings in this regard? Well, obviously we can fix the leaks, but we can reduce our system pressure. To do that, we might need extra storage. We need to look at perhaps our distribution pipe work. Is it the right size? Have we connected up a ring main, or is it just a one-way distribution line? Have you got the right backup capacity in place? Okay, and all in all, it's about looking at how I manage my system and how I manage my insurance. So let's move on to inappropriate uses of compressed air. These are what I like to refer to as compressed air shortcuts. So we're talking about where we're cooling bearings down with compressed air, agitating tanks, air lancers for blowing material around, vacuum generators, pneumatic conveying, as we've already mentioned, drying, cleaning, personal cooling is an all-time favourite of mine. Now you might argue that if you've got a bearing that's really, really expensive and you can't shut down to replace it as a short-term interim measure, you might pump some compressed air in to cool it. Now the danger, of course, with that is what becomes or starts out as a short-term filler or stopgap measure to keep the plant running very quickly over time evolves into business as usual, and before you know it, you need another air compressor. So it's really important, happy to acknowledge there are times when you might need to do these things as an interim stopgap, but it's very, very important that these things don't become part of our business culture or business as usual. Okay, so it's worth sort of going back and thinking and talking about, well, why does this actually happen? Well, there are true cost and time pressures here. Capital costs of dedicated vacuum systems as opposed to just plugging into compressed air is a good one. Time, might not have had time, so it was looking for the quick, easy win we needed to keep the plant running. The great thing is the compressed air system's already there, the infrastructure's there, it's easy to tap in and use a bit more air. It's an easy, I call it a lazy solution. The great thing with compressed air is you don't need an electrician. You don't need another connection at the MCC to hook up another piece of kit. And the other thing, of course, is generally speaking, everyone ignores the fact that there is still a capacity constraint. So we have this perceived no problems, plenty of air, no capacity constraint. When in reality, what we're doing is we're making it somebody else's problem, because at some point you will run out of compressed air. So how do we address this wastage? Well, it comes back to education and training. We need to be able to provide suitable alternatives. You can eliminate the access, improve standards, workplace practices, and really it's about changing the culture. Now, there's plenty of help available through ECA, ourselves. There's people out there that can provide some assistance and help you to identify these opportunities. I'm aware of a site just this year actually that eliminated compressed air being used where it didn't need to be. They didn't even need to replace it. They actually had an improvement in quality, and they reduced their air use by over 30% at no capital cost. Just by asking the right questions and proving that it was a viable alternative, not only did they actually reduce their power consumption, they actually had an improvement in quality. Okay, so just on this point, we've just had a question come in from Tony. Are you mic'd up, Tony? Are you there, Tony? No, not mic'd up. Okay. So Tony's question is using compressed air to produce a vacuum a cost-effective solution? Well, the short answer is no, typically. If you're generating a vacuum, you are generally going to use probably 3 to 4 times the energy, depending on the application, to generate that vacuum with compressed air as opposed to a dedicated vacuum pump. It's something that we'll, in future webinars, we'll go into a little bit more detail. Today's really just about a general overview, but no, it's a very good question. Dedicated vacuum pumps will always, always is a strong word, but in most instances will be a far superior solution. Okay, now here's a really good example. It's not a vacuum pump, it's a blower. Okay, so this was a large site. It was actually in Australia, not here in New Zealand, but there's plenty of similar instances. So what we had is the site was capitally constrained, and on the right hand side there you can see a 37 kilowatt blower. It was used to regen sand filters for their water treatment plant. Now the blower broke down and an emergency substitution was required, and so they had plenty of compressed air available, so they tapped in and used compressed air. So they had 7 bar compressed air, obviously was expanded out, let down to a lower pressure, and then used to backflush the filters. Now the dilemma was, even though this wasn't a continuous use application, okay, what ended up happening is the air worked, and so they thought, fantastic, we can save money in our R&M budget on the maintenance side of things. We don't need to repair the blower. The problem is the blower cost about $32,000 per annum to run. The new compressed air solution used over 200 kilowatts of compressed air. It meant an extra compressor was running that wouldn't otherwise have run. And so just in an energy cost alone, it was $175,000 per annum. So you can see a substantial increase in the cost of the business, and in fact the energy spend would have paid for a brand new blower and far less than the current operating year. So it was a really good example of how the capital constraints on the site meant that their OPEX was substantially higher than it needed to be. And so this example we talked about earlier of bridging the gap between the energy budget and the R&M budget and having the right feedback mechanisms in place becomes absolutely necessary. Okay, here's another really good example. Vortex amplifiers are a great solution rather than just using compressed air, so you can get a sort of a 20-to-1 amplification. Now in this particular instance, they were using compressed air to blow across this conveyor and blow excess bits of plastic wrapping off equipment before it went into a freezer. Now, in actual fact, the simplest solution was just to use a couple of watts of fan. It didn't need a huge amount of pressure, it just needed a bit of air to blow the plastic out of the way. You're talking an 80 to 90% reduction in demand. For this little one application, it was a $12,000 per annum saving. The payback was under a month. You know, it was such an easy gimme, but it was just, we had half a dozen quarter-inch compressed air. They were little push-fit fittings with no tube pushed in the end, just blowing air across the conveyor. You know, it's just a horrendous waste of air. Here's another really good example. You see these little dusters, and this particular one had been taped permanently open and on. And of course, you know, just a really, really bad application. Another one here where there was actually a pinhole leak in a manifold that had been welded, and a number of people actually took the time to mark it up and poke fun at the poor old welder, but no one took the time to do anything about fixing it. So, you know, sometimes it's deliberate, other times our attitudes are as much the problem. Okay, yes, someone mucked up, but who's going to do something about fixing the problem? Now, we just want to take a couple of minutes at this point just to talk about leak rates. Now, some of you will have seen this chart or various forms of it kicking around. And so what we have down here is the pressure. I apologize, it's in American units. So 100 psi is sort of a typical sort of 6.5, 7 bar line pressure. If you go across sort of a 1/4 inch tube, you think, oh gee, one of those flapping in the breeze is 104 CFM. To give you an idea of scale, that ends up being $10,000 to $15,000 per annum in actual power usage. Now, the problem, of course, with this is the 1/4 inch is actually assuming that it's a 1/4 inch hole, when a 1/4 inch tube is actually the OD, not the ID. And so if we go back, instead of actually looking at the 1/4 inch number, we need to come down a size, and it's actually sort of part way between these two, and you end up at about 50 CFM. Now, the other thing, of course, is generally those tubes have some length to it. They're not just a straight hole. That chart is for a hole in the size of a rather large pipe. So when you add length to tube, the loss rate drops dramatically. And so if we can highlight this for you, on the left-hand side there we have a ratio of the loss versus what's on the chart, so 1 being the full amount. So if you have a hole in a pipe, you're going to lose 100%. What's interesting, if you go to a meter tube length, you drop to 1/2. So if we go back to our chart, if we grab our little highlighter here, okay, remember we were sort of in the middle here, okay, at the 50 odd CFM. A 1 meter length tube is going to mean that actually that then drops to 25 CFM, and so where we thought we were at 100, we're actually only at 25. Okay, let me just erase that. Okay, and then as we extend the length of our tube, that rate drops off immensely, and it's not uncommon to be in the 20 to 15% range. And so what started out as being an assumed 100 CFM loss very quickly becomes sort of a 10 CFM loss or less. So it's very important that we don't overestimate and get carried away. They're still worth fixing, just not a $12,000 to $15,000 fix. It becomes a $1,000 to $2,000 fix instead. Still worth doing in most instances. Now, moving on to peak load management. Okay, what do we really mean here? We're talking about balancing our peaks in demand. Couple of really good examples: a baghouse pulsing, cleaning air where we clean down all of a sudden and have air lances coming on and off, purge air where we're purging systems. Now, what are the solutions to these scenarios? Well, obviously one of the big risks with the baghouse pulsing is if your Goyen valve that's used to generate the pulse actually sticks open, which can happen fairly regularly. It's very easy for those things to drain your air system very quickly. So you want to have additional storage at the point of use and sort of non-return systems in place so we can't drain the whole system. There's some really good products on the market now where you can have cut-off switches. If the pressure drops to a certain point, it will then isolate the rest of the system, and then obviously you have an alarm on your baghouse, and then you need to obviously go and fix it. Now, you might not be able to do that if it's a safety risk of having the baghouse to pulse, but there are things that you can put in place, mitigation factors to think about. So obviously regulating your receiver outlet, not the inlet. You want your storage to be at the highest pressure possible. And the pressure-based oscillation valves that we just sort of talked about. So there's a number of things you can look at to do this. Now, here's a really good example. So here's some real plant data. We have airflow on our vertical axis here, and then time. And so you can see it's very, very peaky. You can sort of see an underlying base load there between 50 and 100 cubic meters an hour, and see it's peaking up to nearly 3 times that. Now what we do, here is we like to represent this data a little bit differently, and it's what we refer to as a cumulative frequency graph. And so what we're doing is we're looking at a percentage of time that the flow rate is above a certain level, and you can see that the very peaky nature of this pulsing comes through. And obviously we want to have adequate storage locally so we don't have that peak in demand. We want to actually average that out. Makes a big difference. Now, I'm going to try and, Paul, you've got a question. Are you there, Paul?
Yeah, James. Sorry, just keep going about the bag out, and at the end of it, I'll come in with the comment or question.
Okay, all right. Well, we'll wait for you to get back to us, eh?
Yeah, just when you...
Okay, we'll talk to you in a minute. Okay, so here's another example. So you can sort of see we've got a fairly steady base load, and then you get to the end of the day and some cleaning kicks in. You can see these really nasty spikes. Now, what's caused those spikes, of course, has been people blowing things down with compressed air. Now, there's the obvious safety issues with doing this in creating all sorts of mess and airborne materials and breathing problems and so forth, never mind the energy waste. So once again, if we sort this, you'll see you've got your steady demand, and then all of this over here is your artificial peak associated with your cleaning. Now, in most instances, you would argue quite strongly, in fact, that that should be eliminated, and then an alternative cleaning solution should be identified. So as you address these sort of peak demands, you'll find that your need to have excess system pressure to cope for when your demand kicks in, because when that demand spikes, it immediately is manifest in a reduction in your line pressure. Now, as you eliminate that excess demand, you're getting rid of your artificial demand, you eliminate your inappropriate use, you get good local storage size for your peak demands. As you do that, you can then look at your compressor control strategy. So you've got things like local pressure alarms, you've got system pressure controls, bit of feed forward control if you need to be able to bring a compressor on as required. Then as you do all that, you can reduce your risk or eliminate or minimize your risk as you lower your system pressure. And so as you can do that, you're going to reduce your demand, reduce your losses from your leaks, and obviously your power consumption at your compressor is going to go down because your pressure ratio is less, so you're going to get a net gain in your efficiency on the supply side. So in summary, on the demand side, we can start with leaks. When we want to look at all significant air use that should be pressure regulated, we want to use local receivers with outlet pressure control where we need to, reduce or eliminate all inappropriate uses, balance peak demands, increase point of use storage, identify whether peak demands are really necessary, which can be substituted, eliminated, okay, and can we manage the size of those peaks? Can we reduce them, lower them in some way? Okay, and then ultimately, as you do all that, you can lower your system pressure and make the additional savings at the supply side. Now, what we want to do now is address just very briefly today the supply side of the equation. So we've got things like compressor selection, compressor sizing, compressor controls, ancillary equipment, so your dryers and your filters, where you're storing your air and so forth. The ambient conditions of your compressor house become very important. If you undersize your inlet filter to the air compressor, it means two things. One, it's going to block up a lot more quickly. Secondly, you're going to have a larger pressure drop across it, which means although you've got an outside ambient air pressure, the inlet air pressure to the compressor can actually be quite a bit less, which means the compressor has to work that much harder to produce your compressed air at the desired pressure. So same thing applies if you've got a hot inlet or a humid inlet, then you're sucking in more moisture that then has to be compressed and taken out. Obviously air is hotter, is less dense, so once again you've got to suck more air in. So all of the ambient conditions can have an impact in the plant room. Then of course the big one is, have you got your system specifications right? Are you drying the air correctly? Are you over drying it? Are you spending more money on drying, be it desiccant dryers or otherwise? Now all of these things, when you get them right, can lead to capital savings, energy savings, greenhouse gas emissions reductions, and maintenance savings. Now something that we want to talk about very, very briefly is to just highlight today. We'll go through these sorts of opportunities in more detail in future webinars, but something for you to think about and be asking questions about is, what is your kilowatts per unit volume of air produced, or the specific power consumption? Now you'll have a what you might call a nameplate number, but does that actually account for all of your upstream filtration and all the other ancillary loading, cooling fans, etc.? What is your actual true power consumption per unit of air produced? Okay, you need to be careful that you're comparing apples with apples. Are they with the same reference conditions for your airflow and inlet conditions and so forth? Is it input power or shaft power? Is the motor efficiencies taken into account, etc., etc.? Then you need to look at what your average versus your peak power consumption is. Now, just a note here, and we've got a little example we'll share in just a minute, is don't assume the output flow for the compressor. It's not always the case, and we'll share a really good example of that in just a minute. What sort of pressure stability do you need? How much availability do you need on your system? Do you need complete redundancy? Then in terms of your supplier side of the system, you're going to have power used to make air, i.e. your loaded power consumption. Then a lot of compressors, depending on how you're running and operating them, they might have a substantial unloaded running component where your compressor's ticking over but not producing any air. You might have excessive specific power consumption because the compressor's old and worn, it's got other losses. Your control strategy, especially if you're using modulating control, will mean that your effective efficiency is nowhere near where it should be. So there's quite a number of benchmarks on the supply side to look at. Now bear in mind, of course, all of this is prefaced on, it is all prefaced on us looking at and addressing the demand side first. So as we mentioned earlier, critical review of minimum specifications. What's your pressure requirements? What's your dew point? Are we over drying air beyond what we need to? What sort of reliability or risk level are you prepared to tolerate? Do you need to have complete redundancy, or can you have, if you've got two machines that are running, are you happy to have just one backup machine and plan and hope that not both machines are going to go down together? Okay, so identify opportunities to reduce or eliminate non-productive demand. So this is where if you've got part of the site might not be running around the clock, so can you isolate that part of the site rather than having everything running continuously? Do you need to use portable units as an alternative? A really good example actually was a large site in Australia that had a couple of megawatts of compressed air used, and there was a substantial leak rate of about 500 kilowatts as a base load, and it was largely due to an old site, hard to fix all the leaks, etc. What was interesting though was the site was only used 50% of the time, sort of 2 shifts a day, 5 days a week. Now what was interesting in all of this is outside those shifts they had a lot of maintenance work that was done, and of course depending on where they were in the factory or plant, they needed access to compressed air to do some of their maintenance tasks. So as a result, the compressed air system was largely kept on so that they had access to compressed air for their maintenance strategies. Now, when we sort of sat down and identified this and talked them through it and said, look, okay, you might not be able to fix all these leaks, but you can eliminate half of them just by turning the air off when the plant's not being used. To which they replied, well, they needed the air to perform their maintenance. We then responded back and well, why don't you have a number of portable compressors around the various parts of the plant that you can use as a point of use requirement? As it actually turns out, when they went back and looked, they were already in place. So not only was the saving substantial, they didn't actually have to invest in any of the units. They were already installed throughout the factory. It's just that they'd been forgotten about and left under benches. So, I mean, there are opportunities where you just need to think outside the box a little bit and establish that there are times when there's more cost-effective ways to deliver air rather than using your dedicated system all of the time. Another example, just that last point there, is looking at alternative feeds for fire systems. A lot of fire systems require air where valves fail open in the case of losing compressed air. Do you need to run your whole air system to keep pressure on your fire system, or can a small little dedicated unit do it with an appropriate isolation valve? These can be far more cost-effective solutions. Now, we just got another question here. I'll just Nicholas, are you there?
Yes, can you hear me?
I can hear you well. Yeah. So for everyone, do you want to repeat your question, please?
So my question is, how do you reduce dew point variability out of a desiccant air dryer?
Sure. Okay. So I guess it depends on the nature of the desiccant dryer, but I'm going to assume you're talking about some sort of dew point control being fitted to the dryer, correct?
Yes.
Okay. So if that's being the case, then generally, depending on how the dryer, the towers are being regenerated, the purpose of that is you're going to sense your dew point, and then as the desiccant's no longer able to maintain the dew point, the dryer will then switch. Now, once you do that, your desiccant's going to be regenerated, whether it's by heat, electrical heating, steam regeneration, or it might be just purge air going through. But either way, you'll be regenerating the desiccant, and then you'll start again. Now, the reality is when you start again, your dew point is going to be that much lower, obviously, and then as the desiccant starts to pick up the moisture and become wetter, it's going to deliver a sort of a higher dew point till you get to your set point. So the reality is it's very difficult to stop that variability. It's not like a variable speed compressor that can vary its speed to give you a steady output. Your dew point's going to change just by virtue of the as your desiccant starts to get saturated. So are you talking about that sort of variability, or being able to maintain a minimum set point?
Yeah, I was referring to a maximum set point.
So what do you mean by maximum set point? You're saying?
So, we're talking about the maximum dew point of the air coming out of the desiccant, and maintaining that dew point below that set level.
So you're obviously from a plant that's looking to make pharmaceutical grade products. So your requirement is what, sort of minus 30, minus 40 degree dew point?
The standard is recommendation minus 40, absolute maximum minus 20.
Okay, so are you trying to control to minus 40 or control to minus 20?
Well, that's a good question, but to start with, I'd like to have it to avoid the reading drifting too far above the set point. So we've got a set point of minus 30 at the moment, but it's sometimes reading as high as 21.
Sure. So yeah, I mean, I'll be happy to have this conversation with you offline. We can talk about it in more detail. But effectively, you do need to be mindful, and this is important while we talk about getting your critical review of your minimum specifications. So get to understand what your desired point is as opposed to what your absolute minimum fail-safe point is, and so you want your set point to be, in a dew point case, below that, so that you've got some headroom, and so you need to then control that accordingly, and depending on the nature of the type of dryer, you need to get that right. Now, temperature also becomes important, and having a steady temperature coming out of your compressor, also is quite relevant. But the short answer is you can set those controls up. It depends on the nature of your dryer, but it is about getting the right specification. So very good question. In the interest of time, I'm happy to have a discussion with you offline in more detail, if that's okay.
Sounds good. Thank you.
All right, no, great. Thank you very much. All right, so just carrying on there. So obviously those minimum specifications, as Nick has just raised a really good example, it's important to get that right. Equally, you don't want that dew point, set point to be lower than it needs to be, because then all you're going to do is expend a whole lot of energy over drying your air. So yeah, so it's really important to have a critical consideration of these things. Now, just a quick point on compressor sizing and selection. Once you've sorted out your demand side, looking at your leaks and your artificial demand, inappropriate use, etc., you'll have a good idea of what your actual requirements are, what your storage requirements are, remembering the location of that storage might not be all in the plant room, what backup capacity you need, and just at this point, remember that if you're running around the clock, you need to allow to be able to service your equipment and have additional machines to be able to have one off to be serviced or taken out, redundancy. Now, if you've got the plant off, then you can schedule your servicing in those windows, and that might not be a concern. You've got single compressors versus multiple compressors and how you then interface and control them. There's maintenance and capital costs to consider. Then when it comes to the sizing, you know, there's a lot of people that, as I refer to it, as the poor man's VSD. This is where you might have a whole multiple of identically sized compressors, as opposed to getting the right mix of compressors to better match your demand envelope. And so getting fixed output versus variable output then becomes an important consideration. So we're actually going to go into this in a lot more detail in future webinars, but this is really to get you thinking as you look at your system, remembering we're going to start with demand, but then when we get to the supply side, you need to start asking some of these critical questions. So ultimately, at the end of the day, you've got to bring the whole system together, establish your priorities, plant availability, quality, cost. Now, cost minimization is not just energy. It includes water if you've got a cooling system, maintenance, you've got capital and life cycle costs. Now, you've got minimum performance constraints, but remembering ultimately it's this trade-off of understanding what our demand is and appropriately matching our supply to that demand. So here's an example of some load profiling we used earlier, understanding day shifts, night shifts, weekends, alternative solutions, there's heat recovery options, and a couple of case studies to share with you. So here's a really simple small compressor. For those of you out there with small systems, this is to reiterate that it's not just the big systems where you can save a decent chunk of money. So relatively modest compressor. It was a 37 kilowatt single machine running a system. The average power consumption was 32 kilowatts, but we measured the actual flow rate being delivered and it was fairly modest, looking at the pressure. And so what we realized is the actual demand called for about 11 kilowatts, added a bit of a safety factor, sort of said 15 kilowatts. Now the client at the time was a little bit shocked. They were worried about replacing a 37 kilowatt machine with an 11 kilowatt machine. So they opted with an 18.5 kilowatt VSD compressor. And what you're seeing there is the power consumption when they switched the old compressor off and the new one on. So there was no change in actual demand in the system at all. It was just purely looking at the efficiency of the compressor. To put that in perspective, it saved them over $17,000 in annual power savings, never mind the substantial capital cost saving on this much smaller compressor. And all of that cost was $3,000 at the time of purchasing the compressor to get it right. So even on a fairly modest solution, the opportunities are there. So in summary, on the savings on the supply side, our saving summary is getting the right selection of the compressor technology to suit our demand profile, minimize unloaded running, maintain good compressor efficiency. We don't want to be blowing off compressed air. We want to have sound compressor control strategies, good housekeeping, limit inlet temperature to the compressor, limit inlet humidity, minimize inlet filter losses, and always stop to review the big picture of how all of this fits together. So really it's about systematically going through, once again to reiterate again, starting with the demand side and then going through to the supply side. Now, where to from here? Obviously, there's some great resources available on the Eka Business website. You can get advice and support from your Eka account manager. If you don't have an Eka account manager, get a hold of Eka and I'm sure they'll find someone for you. And just a reminder that the webinar for today will be available via the Eka website and our own website, energyefficiency.nz.com. And just to a bit of an advert for next year, the webinars are starting up in February on the 3rd with pump systems, the 17th is fan systems, and I know there's been a lot of interest on the 2nd of March. We have David Addison who's going to be joining us for a boiler chemistry webinar. So those links to register will be up on the website in the next couple of days, and we'll obviously be advertising them in the new year. Now, just as we finish up, Paul, I'm happy to come back to you guys with your question on your bag houses. You there still?
Okay, can you hear me?
Yep, no, we've got you there.
Yeah, okay. James, no, just thinking of the overall energy saving for baghouse systems, because we've got a lot of baghouse systems on site, as you're probably aware, and a relatively new baghouse we had fitted with some Dillaval nozzles, or Venturi, or some people call them Sonic nozzles.
Yes.
And I'm just wondering if you've seen any cases for retrofitting standard pulse jet blow tubes and adding Venturi nozzles, because they're quite pricey as per nozzle, and you've got lots of nozzles. And I've seen cases, because obviously if your bag DPs are lower, then the total system energy for your ID fans reduce. So so just wondering if you've seen anything or any articles on that.
I haven't, but what you're saying makes good sense. And in principle, this is a really good example of when we talk about peak load management and sort of demand management, this is sort of really the next level up where, okay, you deal with your leaks and all your other wastages, and then you look at where the air's being used, and that's where it's back to what's the business case, and this is where you'd have to look and say, well, my demand is currently this. If I switch to this other nozzle, is it more efficient? I.e. it's going to use less air, but then also does it clean my bag better? And these are all the considerations, and as you rightly point out, it could lead to a better load on your ID fan. Now, it could do one of two things, either reduce your energy bill, or if that's your bottleneck, could free up capacity, which is where you can really make some money. So it really does come back to, you need to do the proper review of the system. If I jump back a couple of slides here. Oh, sorry, wrong way. Where are we? So, when we talk about a total systems approach, this is really what we're talking about, is it's going to that next level of understanding, and this is where, okay, those valves might be a little bit pricier, but there could be a good business case for it. Now, it could be that the first step would be to only stock the new types of valves and install them as they go, or you could look to do a replacement bit by bit. Generally speaking, in a retrofit situation, my general feel in most instances, you'll probably struggle for the energy cost alone to pay for it. Because if you've got valves already in there that are kind of working, you've got to pay for the full cost. Now, on a new build, if you change the specification, the marginal cost becomes a no-brainer. On a retrofit, what you'll probably need to do is it's the additional spillover benefits. So like you mentioned, the loading on the ID fan, be it reduced energy loading, it could be that you can slow the thing down, so then you've got less risk in terms of a maintenance. Everything's running at a slower speed, so your bearing loads go down, your vibration levels go down, all those sorts of things. Or the other thing you could look at is it might be actually we can leave the fan as it is, but we can get more capacity depending on the nature of your system. And it's those sort of added benefits that you'll probably need to get the project close to happening.
Yeah, well, look, I think it's an important consideration, because there's also things like the retrofit because normal pulse jet bag gases, they just have blow tubes. You've basically got to take the blow tube out,
Yep.
modify it. You've got to actually tap a thread into the discharge orifice and put in the nozzle.
Yes.
And then you've probably got to lift the blow tube up, because the idea of the de Laval nozzle is that it can train secondary air, so you get a nice snappy parcel of air travelling down the bag to dislodge the dust particles, the filter cake. So yeah, it is. That's why I was wondering if there's been any, if you've come across, because I know you deal with extensive companies, etc. But yeah, as you say, it's probably better to, when you're speccing a new bag house. The problem is sometimes you get bag houses and you're lumbered with them for years. I mean, we've got here the bag houses have been operating for 30 years, with huge energy costs.
Yeah, well, I mean, this is where I don't want to, you can talk about, what to do, but this is where ECA might be able to assist in terms of there's roles to play, and giving you assistance in terms of navigating that and sort of doing some of the analysis and figuring that out. Support perhaps around sort of some possible trials, maybe depending on the size and scale of the business, and how that can be shared. I don't want to talk for ECA, but that's certainly the sort of thing that I'd be encouraging you to flag with your ECA account manager. I mean, we're certainly always available to assist where necessary and helping you to sort of navigate some of those processes. But and there are other auditors and the like out there that would, I'm sure, likewise be happy to. But yeah, it really does come back, as you say, when it's not just the nozzle, it's everything else around it and what then's wrapped up in all of that. But yeah, so this is where generally my experience would be is it's a no-brainer on a new build, but on an existing system, you're really looking for that sort of double win to sort of really get it over the line. And it's not to say it's not there, because in many instances it is, but it really comes back to the nature of your installation. Then of course you've got the other aspect of you've got a system that's working now. You've got a risk profile associated with making a modification. Does it deliver what you think it's going to, and so on. So yeah, there's lots to throw into the pot. So, yeah.
Okay, thanks, James.
No, appreciate your input today, guys. Just going through just a couple other questions. Here's a good one from Pramesh. I'm gonna let him ask the question if he's. Where are you, Pramesh? Are you there, Pramesh? Are you mic'd up? Pramesh, are you there? No?
Yeah, I can hear you. Can you hear me?
Yeah, no, we can hear you. Would you like to pose your question to the group?
Oh, you just wanted to sort of ask the ultimate question. Should we be working towards a goal of zero compressed air on manufacturing sites? Because I know it's quite an expensive utility, and maybe making that a goal for energy managers should be something that's worthwhile pursuing.
A zero is an interesting target, because I guess when you look at instrumentation and instrument air systems, you could potentially replace a whole lot of equipment with electrically actuated devices. You start to use up quite large currents to actuate some things under some pressure, so it's a tricky one. I wouldn't say I wouldn't rule it out of hand. I think it would be quite a technical challenge for a number of industries. But I think certainly as a very tangible goal, though, I think most sites could look at seriously their demand and say, look, why couldn't we cut our demand in half? There's a whole lot that you could do. Maybe zero might be a little bit of a stretch to start with. But there's a whole lot of air that's probably used that shouldn't be. So yeah, I would suggest that zero is probably an ambitious target, but depending on the site's maturity, I think setting a real target and working towards it's a good goal to have.
Yeah, thanks, James. Yeah, and
Okay.
I know I've come across various clients where they have basically are using the compressed air for inappropriate things, as you say.
Yes.
You know, sort of trying to keep dust out of bearings, or trying to pressurize their MCC switch rooms and things like that. So really,
Yeah, certainly all of those applications absolutely, should be eliminated. No question.
yeah,
Yeah, no, appreciate it. Now, just as we go, we've just had more a comment than a question, and I'm happy to reiterate it from Tony here, saying that in a lot of bag houses that we've been talking about, there's often not a lot of storage close by, which is not very helpful, and also not having them supplied by a ring main. So, getting distribution to these large users with peak loads can become quite important. Now, just on this note, I'm happy to stay on the line for a few more minutes if anyone else has any questions. Having said that, if there are any more questions, I'm welcome to have them emailed through. And as I said, we'll be posting this this broadcast in the next day or two via the ECA website. So I'll give you guys another minute or two, and otherwise we'll sign off today and see you all in the new year. And I guess with that in mind, we wish everybody all the best for the Christmas New Year season. Hope everyone has a safe break and everyone is able to join us in the new year. So on that note, we will sign off and wish you all the best, and we will see you again on the 3rd of February next year.